Hi everyone, welcome back to my channel. In this video, I am going to show how to design and simulate a PV with incremental conductance MPPT connected to a boost converter and battery charging system using MATLAB and simulation. I will walk you step by step through how to model a PV panel under different irradiance, then after that boost converter, then after that battery, and also incremental conductance MPPT. So let's discuss about first one, PV panel with a different irradiance level. So here you can see my PV module in Simulink. I'm applying different irradiance level. For example, I chose for 1000 irradiance level, I'm getting the maximum power is equal to 213.15 watts at the voltage of 29. Similarly, for 800 irradiance level, I'm getting 171.79 watts at the voltage of 29. Similarly, for 600 irradiance level, I'm getting the maximum power is equal to 129.509 watts at voltage of 29.334. As irradiance decreases, you will notice that the power also reduces. That is mean by with respect to the PV current, if PV current is decreases, PV power also decreases. So therefore, the maximum power point is shift at every conditions. So this is exactly why we need MPPT to ensure we always extract the maximum possible power regardless of sunlight changes. Okay. Next, we move to how to design a boost converter. So let's see here, the open circuit voltages of PV panel is equal to nearly 36.3 voltage. So this is the input voltage of the PV panel to the boost converter. So you can see that the output voltage of the battery is equal to nearly 48 voltage. So therefore the input voltage is lower than the output voltage. So we need boost converter to boost up the input voltage to the battery side circuit. So therefore, I have designed a boost converter. So the purpose of boost converter is to step up the PV voltage to higher suitable battery charging. So I have already explained how to design a boost converter design, including inductor selection, capacitor selection, a duty cycle equation, and also switching frequency. So this converter is controlled by the duty cycle, which will be continuously updated by the MPPT algorithm to match the PV maximum power point. So I'm just showing the implemented model. Inductance value, capacitance value, I already calculated with the help of this coding. I already shown in that video. You can refer that video. Okay. Then after that, this boost converter output is connected to the battery circuit. So I choose here lead acid battery. The nominal voltage is 48. The rated capacity of battery is equal to 200 amperes per hour. The initial state of charge is equal to 45%. Now let's come to the to how to extract the maximum power from the incremental conductance MPPT. Here I have attached two types of incremental conductance MPPT model. The first one is I take the delayed value from the outside of the my MATLAB function, that is delayed by one sample of the current sample. This V and I is referred as the current instant values from the solar PV voltage and also current. Then after that, here I calculated the value of D. It is also delayed by one sample with the help of delay. Similarly, V0 and also I0 also I am calculated with respect to one delay samples. As we discussed earlier, how to model a incremental conductance MPPT with the help of PV curve. The first step is to measure the PV voltages and also current. After that, we need to calculate the value of del V. Here I represent the del V as a dV is equal to V minus V0. Similarly, di is equal to nothing but del I is nothing but I minus I0. V is nothing but a current instantaneous value from the PV voltage, and I is nothing but a current instantaneous current from the PV panel. The V0 and also I0 is referred by the delayed by one sample, is nothing but the previous sample. Then after that, I consider the duty cycle in earlier small changes in D is equal to 0.05. Let's come into the statement conditions. When dV is equal to 0, if the condition is satisfied, then we need to calculate the fact dI is equal to 0. If both the conditions are satisfied, then duty cycle will be D taken as a final value. If this condition is not satisfied, whether we need to check whether it is appear dI is greater than or 0 or less than 0. If dI is greater than 0, we need to reduce the duty cycle to increase the voltage. Similarly, if dI is less than 0, the duty cycle to reduce the PV voltage. This is the statement 1. If dV is not equal to 0, then we coming to the next condition, that is in by dI divided by dV is equal to minus I divided by V. We want to check this value. If this value is satisfied, then this value will be considered final duty cycle M is equal to D. Then if this condition is not satisfied, we need to check whether it is appear on greater than minus I by V or less than minus I by V. If the condition is greater than minus I by V, we want to reduce the duty cycle to increase the PV voltage to attain the maximum power. Similarly, if this condition is not satisfied, then increase the duty cycle to reduce the PV voltage to attain the maximum power. So, if the conditions are satisfied, that corresponding will be taken to the final value of duty cycle. So this is a coding for our corresponding flowchart as we discussed in that video. You can refer that link to how to model that equation. So this one kind of method I use the delayed sequence in outsides. So this is the second my incremental conductance MPPT. You can see here I already taken the previous voltage samples and current samples in coding itself, and also I choose D is equal to 0.5 for initial duty cycle. Then after that delta D I choose as 0.05. The once we measure the PV voltage and current, then we move to the del V and also del I. Then after that coming to the statement, if dV is equal to 0 and also we calculate dI is equal to 0, you take the final duty cycle is equal to previous one. If this condition is not met, we need to increase or reduce the duty cycle. Coming to the next condition, if instantaneous conductance dI divided by dV is equal to minus I divided by V. If this condition is satisfied, then it will be maximum power point, that is maybe D is equal to that corresponding duty cycle. If this condition is not satisfied, that is mean by dI divided by dV is greater than minus I by V, we need to reduce the duty cycle to increase the PV voltage to attain the maximum power. If this condition is not satisfied, we need to increase the duty cycle to reduce the voltage to attain the maximum power. Then after that, we use the duty cycle limits. If D is greater than 0.98, it is considered as a D is equal to 0.98, because we want to consider the duty cycle is less than 1. Then after that, if D is less than 0.2, we want to take D is equal to 0.2. Then previous sample is updated in each iteration, that is V previous is equal to VPV, and also I previous is equal to IPV. Final D previous duty cycle previous value will be taken as a final value of D. Let's simulate our simulation. I choose a constant irradiance, 1000 irradiance level. So I'm getting for 1000 irradiance level, and the PV power is equal to 212.9 watts. The battery power is indicated here negatively because the battery is now currently is what? Charging. You can see that minus 210 watts. The voltage is gradually increasing. That is maybe the battery is charging 47.51 to 47.5 to 53. You can see the PV curve. It attains the maximum power. Let's see the battery power for the constant irradiance level of 1000. So you can observe that the maximum power of the battery side, it's nearly equal to 210 watts. So that's what the exactly maximum power from the PV panel with the help of incremental conductance MPPT. Let me see for different irradiance level how our system will be work. So I choose here for different irradiance level 1800, 0, 1000 for different time periods. You can see the PV curve as well as battery charge responses. For time period of 0.2, our irradiance level change to 800. So therefore the maximum power extracting from the PV panel will be reduced to 175 watts. You can see that our MPPT will be work accordingly to the program. So the battery power also reduced due to the maximum power extract from the PV panel. You can see it reduced to 200 watts to nearly 175 watts. At 0.3 second, it will be reached to 0 irradiance. At the time, there is no power. Then after that, when it reaches 0.4 second, once again the irradiance changes to 1000. So therefore, the maximum current extracted from the PV panel is equal to 7.35. So therefore, we will get the maximum power up to 215 watts. So this is the extraction of PV panel curves. This one is the extraction of battery curve. You can see the difference between for different irradiance level. So now you can understand how to model the incremental conductance MPPT algorithm for our design with the help of boost converter with the battery charging system. So this system is ideal for solar charging applications, standalone PV system and renewable energy research. If you found this video is helpful, please like, share and subscribe. Thanks for watching and see you in next video.